Good morning. Am I audible? Good
Yes,
morning.
ma'am.
Good morning, ma'am.
Okay.
Yes,
Okay. I hope you would have received the notes by now, which has both like one the notes, handwritten notes, and the other one is textbook Xerox. Okay. Whichever is okay for you, you can refer, or any other textbooks also you can refer. Okay. Whichever was available with me, I have just sent you whichever topic in which textbook you can understand from that. I have just taken it. Fine. So next chapter, that is fifth unit, pH buffers and isotonic solution. Before we go on, anybody, what do you mean by, I'll stop this so that you'll answer. So according to you people, what do you mean by pH? I hope I'm audible.
ma'am. It's a scale. Yes,
Yeah.
ma'am. It's a scale where we can measure the acidity or the basicity of a solution.
Okay, very good. Then any other answers other than what he has answered? pH, according to him, pH is a scale which is a measure of acidity or basicity. Okay, other than that,
Ma'am, it's a negative logarithm of the hydrogen ion concentration.
very good. Then anybody else? This is the actual definition of pH, negative logarithm of hydrogen ion concentration. Okay, then anybody else? What do you understand by pH? Anything related you can tell. That's all. Nobody wants to have an attempt of what do you mean by pH? Okay, fine. So we'll consider both the things, both are right. So now what do you mean by an acid? What do you mean by a base? So common to common, till now you would have studied many a times. What's an acid? What's a base?
Acids are the proton donors, ma'am,
Okay. What are bases
and
then?
bases are proton acceptors.
Okay. Okay. Anybody else? Any other different answers other than this? Other than proton donors and proton acceptors? No? All are okay with the same answer? Anybody? Okay. So in general, there are three different theories which explains acid and base on their own. Okay, pH, as you people said, it is negative logarithm of hydrogen and concentration, as well as it's a means of measuring acidity or basicity of a solution. Both are right. Okay, so in general, what exactly is an acid, what exactly is a base? There are three different theories. Three different scientists have their own opinion of what's an acid, what's a base. Okay, so three different theories are, one is Arrhenius theory, second is Bronsted-Lowry theory, and third one is Lewis acid-base theory. Fine, three different theories. According to three different scientists, they have explained acid and base according to themselves. Okay, so there are three different theories which portray what are acid and what are bases. So according to the first, that is Arrhenius theory, an acid is a substance which will give up hydrogen ion readily, and base is a substance which gives hydroxyl ion. Okay, so anything according to Arrhenius theory, any substance which will give hydrogen ion, that is H plus ion or H3O plus ion, is an acid, or anything which will give OH minus ion, or what we call it as hydroxyl ion, are known as bases. So this is on dissociation. Say now you take up a substance and you add it into water. So when you add it into water, they dissociate, obviously, right? Any substance, when you add it into water, will dissociate if it's an electrolyte. So whenever you add it into water on dissociation, if it's giving away H plus ions more, then you are calling it as an acid. And if it's giving OH minus ion, we are going to call it as a base. Clear? This is according to Arrhenius. I hope I'm clear. What is acid and base according to Arrhenius theory? Anybody has any doubt or who didn't understand? I'll repeat if you want. Understood? Am I audible? First thing. Am I
Yes,
audible?
ma'am.
Yeah. You're
Yes, ma'am.
clear? You're clear with what is Arrhenius theory? What is an acid and base according to Arrhenius theory, right? So next is Bronsted-Lowry theory. According to Bronsted-Lowry, what he said was it is mainly depending upon the solvent into which we are adding any substance. So according to Bronsted-Lowry theory, an acid is a substance which can be charged or uncharged, which is capable of donating a proton. This is what was said by today's answer. So anything which is capable of donating a proton is an acid according to Bronsted-Lowry theory, and a base is a substance which is capable of taking up the protons which is given by the acid. Okay, according to Bronsted-Lowry, an acid is a one which will readily give up proton, okay, which is donating proton, and base is a one which is accepting the proton which is given by the acid. Clear? So this could be charged, uncharged, whatever substance we are taking. So that could be charged, having a charge, or it could be without a charge, uncharged ones. But they should be able to give up proton are acids. Those which are readily accepting the protons given by the acid, we are going to call it as an base. Okay. So not only this, other than this, it depends on to call any acid as a strong acid or a strong base. So anyone, what do you mean by a strong acid? What do you mean by a strong base? Or sorry, let me consider only acid or let me consider only base. So when do you call an acid as a strong acid? When do you call an acid as a weak acid according to you people?
Ma'am, strong acids which can dissociate completely, ma'am.
Okay, what's a weak acid then?
Ma'am, which leaves the residue, ma'am.
In the sense, which leaves residue in the sense? Can you please elaborate? What do you mean by which will leave residue?
It doesn't dissociate completely, ma'am. There
Right.
are
Yes, go on. There are.
not getting the particular word to it.
Okay, no problem. You are right. So they partially dissociate, right? So in general, we have to, if at all, if we have to say, so an acid is a strong acid is the one which will dissociate completely. Okay, say now we had 20 molecules of an substance known as X. Okay, so X on adding it to water, it is dissociating into two different products. Okay, since we consider 20, 10 each is going to get dissociated. Clear? So this is an example of a strong acid. We had 20 molecules which has got dissociated into 10 each. Okay. Yes, who is it?
Yes, ma'am.
Okay. So so if we consider, as I gave an example again, 20 molecules if you are considering, when you add it into any, generally I'm talking water, I'll tell you why. So when you add it into water, if it's dissociating into 10 each molecules, so complete dissociation has taken place, so which we call it as a strong acid. Same 20 molecules assume have taken as Y, okay. Y is a weak acid, I'm telling. Why? I'll tell you. So this particular Y molecule is dissociating to form, say, 5 molecules each of. That is, it is getting dissociated into 5 each, and still dissociation is taking place. Okay, it is partial dissociation. It's not completely dissociating into respective ions. So since we had taken 20 molecules, we are expecting 10 each as a product. But we are getting less than that because complete dissociation has not yet taken place. It will happen, it will take a very long time for it to happen, or it does not happen at all. And again, to call an acid as a weak acid or a strong acid, it depends on the solvent into which we are adding it. Make it very clear. Any acid or a base, we call it as a weak acid or a weak base based on into which solution or solvent we are adding that particular acid into. For example, same has been told here. The relative strength of an acid and base is measured by the tendencies of these substances to give up or take up proton. Say now, any substance is able to give up proton readily. As I gave example, 20 molecules. So that we are going to call it as a strong acid. And since it is taking up the proton, the base, so we will call it as a strong base. Not only this, example, HCl is a strong acid. All of you are okay with this? HCl is a strong acid in water because HCl on dissociation gives H plus ion and Cl minus ion. Since single molecule of acid is giving single H plus ion, it's a strong acid, right? This is only in case when we add it into water. Okay, same thing is mentioned here, whereas same HCl, which we are going to call it as a strong acid, when you add it into acetic acid, okay, when you add it into acetic acid, it is going to give slowly the ion. That is, HCl is a strong acid in water because it gives up proton readily, whereas acetic acid is a weak acid because it gives up its proton only to a small extent in general. Okay, we're going to call HCl as a strong acid because it readily gives up H plus ion. H plus ion on adding into water, and acetic acid in general we call it as a weak acid because it does not give proton readily as in case of HCl. So slowly, only to a certain extent it gives up the H plus ion, because of which we are going to call it as a weak acid. Not only this is one way of calling it as a weak acid or a weak strong acid. The strength of an acid or a base varies with the solvent. As I told earlier, HCl, whatever we said, is a strong acid when we add it into water. But same HCl, when you add it into glacial acetic acid, it becomes a weak acid. Okay, so it depends on two, based on, there are two criteria for calling any acid as a strong acid or a strong base or a weak acid or a weak base. For example, if you are going to call it as anything as a strong acid, it should really readily give the proton. Okay, on adding into any solvent, it should readily give up the proton, then you call it as a strong acid. Okay, so strong base is a one which will accept the protons whenever you add into water. Fine. Not only this, we call anything as a strong acid or a strong base based on into what solvent are we adding that particular acid into. This is the main thing. So in certain solvents, strong, so-called strong acid also behaves as a weak acid, and strong base behaves as a weak base depending upon solvent into which we are adding. As I gave an example, HCl is a strong acid when you are adding into water, but the same HCl becomes a weak acid when you add it into glacial acetic acid. Similarly, acetic acid, which we call it as a weak example of a weak acid, becomes a strong acid when you add it into liquid ammonia. Clear? So the strength of the acid depends not only on the ability to give up the proton readily, but also on the solvent into which we are introducing it. I hope it's clear. Anybody who has any doubt, you can ask. I can repeat if you have not got it. Understood? What's an acid and base according to Bronsted-Lowry theory? And when do we call an acid a strong acid? When do we call a base as strong base? Or when do we call an acid a weak acid? When do we call a base as a weak base? I hope it's clear.
Yes,
Is it clear? Okay, so based on this, as I said, ability of the solvent to take up the proton or take up the based on the ability of the solvent to accept the proton from an acid, we're going to call it as basic strength of the solvent. Okay, so how readily the solvent will be able to accept the proton, so based on that it will be called as basic strength of the solvent. So some examples, since we said Bronsted-Lowry classification or acid or base are the one which could be charged or uncharged. Example for both. So anions such as HSO4 minus, CH3COO minus, cations such as NH4 plus, CH3O plus, or it could be neutral molecules such as HCl or NH3. All these are example of acid and base according to Bronsted and Lowry theory. Okay. Not only this, he calls water as amphiprotic. What do you mean by amphiprotic?
Which acts both as acid and a base.
Right. So water is such example which can behave as an acid as well as a base. How is it? Here we have considered. So acid-base reaction generally occurs between an acid and a base, right? So acid reacts with base to form a new acid and a new base. So because the reaction involves transfer of protons, they are known as proteolytic reaction. I'll tell you. Just imagine HCl, which we call it as an acid. Okay. Don't now assume whether it's a strong acid or a strong base. Okay. HCl, which is an acid, you know it. It's an acid, and water we are considering. So this HCl, whenever you add it into water, what kind of acid it becomes? HCl, when you add it into water, HCl, when you add it into water, what sort of acid does it become?
It becomes a strong acid.
Right. It becomes a strong acid because on adding into water, it is readily giving up H plus ion of
H3O.
from this plus. So this will combine with this to form H3O plus, and Cl minus is as it is. So this Cl minus is a strong base again. So HCl, from HCl, the Cl minus is given out, and from HCl, H plus ion combines with H2O to form H3O plus, which is hydronium ion. Again, it's a strong acid, right? So here, a acid and a base is reacting amongst each other, which results into a formation of another acid and a base. I hope it's clear. An acid and a base. Here water is behaving as a base. Okay. So an acid and a base is reacting amongst each other to form another set of acid and base. Such acid base pair, we call it as conjugate base pairs. Okay, whenever there is a reaction between an acid and base which results into one more set of an acid and base, we're going to call it as conjugate base pair. Amongst this HCl and Cl minus is one conjugate acid base pair. Okay, HCl and Cl minus is one acid base pair, and H2O and H3O plus is one acid base pair. So HCl and Cl minus, we are going to call it as conjugate base pair. H2O and H3O plus, we are going to call it as a conjugate base pair. Is there any doubt?
No doubt.
No. So in general, whatever H plus ion we are going to call, it does not actually exist practically. It's only the hydronium ion or H3O plus ion only which exists. So in that case, so in this particular equation, HCl is an acid which has donated a proton to H2O. That is why it is called as a base. Because it is giving up a proton, you're going to call HCl as an acid. Since H2O in the reaction is taking up the proton given by the acid, you're going to call it as base to form the corresponding acid and a base. Is this clear? Bronsted-Lowry theory? I'll repeat. Bronsted-Lowry theory is a one which says that an acid is a one which will give up protons readily on adding into a solution, and base is the one which are ready to accept the protons which is given by an acid. Okay, so we are going to call any acid as a strong acid if it's able to give up the protons readily on adding into the solution, and base we are going to call it as a strong base whenever it is trying to accept all the protons given by the acid. So this is strong acid and strong base. Fine. So not only this, a strong acid is a one, or strong acid is a one which will dissociate completely to give up the proton, and strong base is a one which will take up the protons given by the acid. So anywhere we are going to call acid or a base depends on the strength of the solvent into which we are going to add the acid or a base. So it depends on the solvent, how readily it is taking up the proton. Based on that, we are going to call an acid as a strong acid or a strong base. For example, a so-called strong acid like HCl becomes a strong acid when you add it into water because it readily dissociates. In that case, acetic acid, when you add it into water, it will partially dissociate. Thereby, we're going to call it as a weak acid, acetic acid, right? Same examples, the strong acids. One second. Sorry. So I was talking about the strength of an acid solvent. So anything we are going to call like the same strong acid, whatever the same acid, whatever we are going to call it as a strong acid, whenever we add it into a solvent like glacial acetic acid becomes a weak acid. The same so-called weak acid, that is acetic acid, when we add it into liquid ammonia, it is behaving as a strong acid. So it not only depends on the availability or how readily they are giving up the proton or accepting the proton, it also depends on the strength of the solvent into which we are introducing the acid or base into. Okay, this is Bronsted-Lowry theory of acid base. Clear? Anybody has any doubt? Any doubt? Are you able to hear me?
Yes, ma'am.
Yes, ma'am.
Okay, I hope it's clear.
Yes, ma'am.
Okay, moving on to next, Lewis electronic theory or Lewis acid base theory. So according to Lewis acid base theory, he tells acid is a molecule which accepts the ions. Ion electron pair which is given by the base. So here, according to Lewis theory, base is a one which is readily sharing up the pair of electron with that of the acid, and acid is a one which is readily accepting the electron pair shared by the base. So totally in general, according to Lewis acid base theory, the ultimate formation or what we call it as the bond formation between the two acid and base is nothing but coordinate bonds, covalent coordinate bond. Where exactly do you observe this covalent coordinate bonds? What sort of molecules have this?
Complexes, ma'am.
Yes, right. So metal complexes, if it specifically have to tell, it is the metal complexes wherein you get the covalent coordinate bond. So according to Lewis electronic theory, so it's the ultimate resulting is nothing but covalent coordinate bond, that is in general it takes place in the metal complexes. So according to him, acid is a one which will be able to take up or which will be able to take up the electron pair which is shared by the base, okay, which is shared by the base, and base is a one which will be sharing an unshared pair of electron with that of the acid. Same thing is mentioned here. According to Lewis theory, an acid is a molecule or an ion that accepts an electron pair to form a covalent bond. A base is a substance that provides a pair of unshared electron by which the base coordinates with an acid. So ultimately leading to covalent coordinate bond. Example, boron trifluoride and aluminum chloride, although do not contain any hydrogen and consequently not serve as proton donors, as in case this is in comparison to Bronsted-Lowry theory. So according to Bronsted-Lowry or Arrhenius, it should give hydrogen ion readily, right? But here, even though boron trifluoride or aluminum chloride, they do not contain any hydrogen, but still they act as an acid. Is it clear? So consequently not serve as proton donors are acid here. So many substances that do not contain hydroxyl ion, including amines, ethers and carboxylic acid and hydrides, are classified as bases according to Lewis way of classifying acid and base. This is an example. So this is a base which has this lone pair of electron which has been shared between this H plus and this, forming a complex coordinate bond, covalent coordinate bond. So this boron trifluoride with that of the anhydride CH3OCH3. So wherein there is a sharing of electron between this oxygen and the boron, forming a complex which is covalent coordinate bond between the boron trifluoride and this. Clear? Clear about different ways of classifying acid and a base? So whatever
Yes,
definitions you
ma'am.
give, all are right. So an acid is a one which will give H plus ion. A base is the one which gives hydroxyl ion, right? This is according to Arrhenius theory, which is right. So according to Bronsted-Lowry theory, an acid is the one which will give up pair of, or which will give up proton, and base is the one which will accept the proton according to Bronsted-Lowry theory. So according to Lewis acid base, an acid is the one which will be taking up the electron pair from the base, and base is the one which will be sharing the lone pair of electron with that of the acid. All three definitions for acid base are right whenever you apply a particular theory for it. Clear? So all three definitions are right. So we'll move ahead with what is pH and all detailing about the pH. So potential of hydrogen. So as I think Tanya answered, so pH is the one which is defined as a negative logarithm of hydrogen ion concentration. So basically pH or acidity or basicity is all about the pH and measurement of the same. Okay, so in general, this pH represents the ratio of hydronium ion to hydroxyl ion. Okay, in general, how much is the H plus ion or H3O plus ion to that of OH minus ion concentration? If it's well balanced, say equal molecules of H3O plus and OH minus are present, then pH becomes neutral. We'll talk about that later. So in general, just remember that we call pH as high, which corresponds to low hydrogen ion concentration, and vice versa. If we say that low pH, that corresponds to high hydrogen ion concentration. I hope you're getting. As the hydrogen ion concentration increases, hydroxyl ion concentration decreases. Okay, it's a balance between H plus ion and OH minus ion. Okay, so if at all, if there is a reduction or the concentration of the hydrogen ion is less, indirectly what happens? Concentration of hydroxide ion increases. Since it's a balance between the two, it depends on which will increase. If hydrogen ion decreases, hydroxide ion increases, wherein the pH will increase. If hydroxide ion increases, pH will increase. If hydrogen ion increases, pH will decrease. So a high pH corresponds to low hydrogen ion concentration and high hydroxide ion concentration. For example, low hydrogen ion concentration in the sense hydroxide ion is more, pH is high, that is it's way beyond 7. It's more than 7. Okay. So we'll talk about that later. So it is not possible actually experimentally to measure what is the activity of a single H plus ion or H3O plus ion. Hence, pH scale is being introduced by the United States as well as Great Britain, which is now we are going to call it as a standard reference for the buffer, which is actually a scale, a arbitrary scale. What do you mean by arbitrary? What do you mean by arbitrary?
Imaginary.
Right. So it's just an imaginary pH scale which we are assuming. So this particular scale of pH which has the values, we are going to call it as pH scale. And there's a particular name for the pH known as Sorensen's pH scale. So we'll talk about that later and how it looks. So before that, we should know what is ionic product of water. Okay. So in general, ionic product of water we represent as Kw. Okay, so just assume one molecule of water can be thought as a weak acid, weak electrolytic solution. As we know, molecule of water can behave as an acid as well as base, right? It is amphiprotic. Thereby, just imagine that one molecule of water can be thought of as a weak electrolytic solute, and that reacts with another molecule of water as a solvent. There's the interaction between solute and solvent, just imagine. So this autoproteolytic reaction is represented like this. One molecule of H2O, which we are assuming it as an acid, another molecule of H2O, which acts as a base. So they are reacting amongst each other, which gives up H2O plus H here, this reaction leading to H3O plus and OH minus ion. Again, there is a formation of an acid and a base. Clear? If we are we are going to call it as equation 1. if we apply law of mass action to this particular equation, what is law of mass action? What is law of mass action? Anybody? Anyone? What do you mean by law of mass action?
No, ma'am.
Nobody knows? At least try to attempt.
Ma'am, is something related to the molecular concentration.
Right? You're right. It is related to molecular concentration. It is nothing but molecular concentration of the product to that of the reactant. Okay, so the product of the, it's nothing but a multiplication of the product whatever has been formed in a reaction to that of the reactant. Molecular concentration of the product to that of molecular concentration of the reactant is nothing but law of mass action. So same thing, molecular concentration of the product when it comes to it is H3O plus and OH minus to that of reactant, that is nothing but two molecules of H2O, that is H2O twice, is equal to K. This is nothing but the constant of law of mass action. Okay. So the term for the molecular water in the denominator is squared because molecular water exists in greater concentration when you compare with the relative concentration of hydroxyl ion as well as hydrogen ion. Okay, so what we are going to do is that we have combined this, and now since H2O2 the molecular concentration is much greater, the amount when you compare it with its product, so we are going to combine these together, that is K along with that H2O the whole twice molecular concentration, and that we are going to call it as a constant. So K along with H2O2 twice is equal to H3O plus into OH minus. So with K, to give a new constant, that is H2O2 combines with the constant K to give a new constant known as Kw, which we are going to call it as a dissociation constant, or also known as ionic product of water. Okay, if at all this we are going to call it as 2, equation 2. Here we are Kw is equal to K into H2O whole twice. That is what we have called, right? We have combined these two constants to give up one more constant known as Kw. Same thing is been written, Kw will be equal to K into H2O whole twice. So now what we are going to do is that we are going to substitute this particular value in equation 2. Okay, this particular value we are going to substitute here. So what do we get? Kw is equal to K, which is equal to H3O plus into OH minus divided by H2